For more than 100 years, physics has been wrestling with a huge problem, a massive gap between how we understand the giant, sweeping cosmos and the totally bizarre world of the super small. Today, we're going to dive into a pretty wild idea that says the secret to connecting them might be in the very fabric of reality itself. What if the universe isn't smooth and elegant, but an infinitely complex fractal code? Let's get into it.
I know. That's a bold question. General relativity, it's one of the most successful theories in the history of science. But what if its most basic assumption, that spacetime is this smooth, continuous fabric, is just an approximation? What if underneath it all lies a much deeper, much rougher reality? A reality that just might hold the key to everything?
So here's our game plan. We'll kick things off with that century-old problem. Then we'll jump into this radical new solution built on fractal geometry. We're going to see how it supposedly derives quantum mechanics from scratch, completely rethinks the vacuum of space, and even finds clues out there on the cosmos, before we look at what this could all mean for the future.
Okay, first up, the fundamental conflict right at the heart of modern physics. You can think of it as a clash of two titans. Both describe our universe with unbelievable accuracy, but they also completely and totally contradict each other.
So on one side, you've got general relativity. It paints this gorgeous picture of a smooth, graceful, geometric universe where spacetime bends and curves. And on the other side, you've got quantum mechanics, which describes a reality that's, well, it's jittery, it's uncertain, it's all based on probability. Now, they both work perfectly fine in their own lane, but the moment you try to bring them together, like to figure out what's going on inside a black hole, the math just falls apart. It's a total disaster. All right, so how do we possibly fix this? Well, this new theory suggests something pretty dramatic. Just throw out the whole assumption of smoothness. What if, at the most fundamental level you can imagine, spacetime is actually infinitely jagged and complex? The key idea here is a mouthful: non-differentiability. But don't worry, it sounds way more complicated than it is. Just think about a coastline. From a satellite, it looks pretty smooth, right? But as you zoom in, you see bays, then you see rocks, then you see individual grains of sand. The closer you look, the more complex and jagged it gets, forever. This theory says space-time is exactly like that. It's continuous, but it's infinitely rough at every single point. And this table just lays out the consequences perfectly. I mean, look at the difference. Classical spacetime is smooth. Fractal spacetime is rough. In the classical world, a particle has one clear path. Here, there's an infinite number of potential paths. But the craziest part, the absolute game changer, is velocity. On a fractal path, a particle has two velocities at every single point, one moving forward in time and one moving backward. All of a sudden, these bizarre quantum rules we just had to accept, they start to look like they're just an inevitable result of the geometry itself. And this brings us to the first huge payoff of this idea. Instead of just accepting the weirdness of quantum mechanics as a bunch of rules we have to live with, this framework says, no, we can derive them. They come directly from the geometry of space itself. So, here's the bottom line. The laws of quantum physics aren't just some arbitrary rules God threw into the universe. They're the logical, unavoidable consequence of moving through a fractal landscape. You could almost say they're the traffic laws for a jagged, infinitely complex universe. So how does this actually work? It's this incredible chain of logic. You start with just one simple premise. Space-time is fractal. That one thing means a particle has two velocities at every point. You can combine those into a single mathematical tool called a complex operator. Then you just ask a simple classical physics question. What's the path of least resistance? And the result is just astounding. The equation that just pops out at the end is the Schrödinger equation, the absolute foundation of quantum mechanics, derived from simple geometry. It's an incredible aha moment. Okay, so if spacetime has this incredibly complex geometric structure, what is it actually made of? The next piece of this theory completely redefines what we think of as empty space. The vacuum, it turns out, might just be the most important thing in the entire universe. This is where we get to the idea of a capacitive vacuum. The theory says we need to just forget the idea of an empty void. Instead, we should picture space as a real physical substance, a dielectric medium that's literally buzzing with energy. It can be polarized and it can store that energy, almost exactly like a capacitor you'd find in an electronic circuit. What this really means is that space isn't empty at all. It's a vast sea of pure potential. And from this one idea, this framework suggests that everything we see and experience is just a ripple, an excitation of this vacuum field. In its most basic state, it's just pure potential. The first derivative, or the first change in that field, gives rise to time itself. The second derivative gives us gravity. And higher order changes, they give us the other fundamental forces of nature. All of physics just emerging from one single underlying field.
So, what does that mean for our old friend gravity? Well, in this model, gravity isn't about the curvature of spacetime anymore. Instead, it's basically a pressure gradient in this vacuum energy. A massive object creates a kind of low pressure zone in the vacuum's potential, and other objects simply get pushed into it, following the path of least resistance.
Okay, this is a beautiful, really elegant theory. But is it science? To be actual science, it has to make predictions we can test. So let's go looking for the fingerprints of this fractal geometry out in the real universe. You know, when we map out the biggest structures in the universe, those huge walls and filaments of galaxies, we find they aren't spread out randomly, and they're not smooth either. They form what we call the cosmic web, and it has a measurable fractal dimension. And what's really fascinating, as this data shows, is that that dimension actually changes depending on how far back in time we look. It suggests the universe's geometric complexity has been evolving for billions of years. 9%. What does that number mean? Well, it represents a huge glaring anomaly in our best map of the early universe, the cosmic microwave background. The problem is, some of the big temperature patterns up there are aligned with our own solar system in a way that should be statistically, almost impossible. It's so weird that astronomers have nicknamed it the axis of evil. But check this out. In the fractal model, this isn't an anomaly at all. It's a fossil. It's a geometric memory from when the universe was born. The primordial fractal structure permanently imprinted on the very first light. What standard cosmology sees as a 1 in a million statistical fluke, this theory sees as a predictable, deterministic echo of the universe's fundamental code. And finally, let's look ahead. Because if this theory turns out to be right, it doesn't just rewrite our physics textbooks. It could completely rewrite our relationship with reality itself. And look, any good theory has to make predictions you can actually test. This one makes several really wild ones, from tiny deviations in gravity at short distances to effects we might be able to see in particle colliders. But the most incredible one has to be the endothermic effect. It predicts a device that would actually get colder as it works, a kind of gravitational refrigerator that converts random heat into ordered gravitational work. It's a clear experimental test that could either prove this whole framework or completely falsify it. Which really brings us to our final mind-bending question. This theory doesn't just describe the universe with laws, it reframes it as a kind of recursive information processing system, a cosmic algorithm. And if that's really what reality is, it raises the ultimate question. Could we one day move beyond just observing the universe and actually start engineering the fabric of space-time itself?